wanted to have my sources ready, just in case.
My sources are my mind.
Um, and here's the other thing. There's nothing wrong with being wrong and being correct in science. If you don't know something, it's easy to just have someone tell you, hey, this is what this is, and we have a nice, civil conversation about it. So I think
Exactly. If you're never wrong, you're not learning new stuff.
Exactly.
I'm okay being wrong. I mean, there's better ways to be pointed out to be wrong than other ways.
Yeah.
But like,
then have people in the comments go like, "Oh, you're wrong. This is why. Here's your actual facts." It's like,
yeah, well, I don't mind that because I feel like, at least when I read it, I have like a gentle undertone to it. It would be like, "Oh, you were wrong, sweetie. Here's the right way to do it," kind of thing.
Like there.
Yeah, basically, like that's the type of voice I'll picture. But like, if someone just goes like, "You're wrong, and this is why you're wrong," like very aggressively,
right,
kind of hurts the message.
Yeah, I agree.
I feel like I'm gonna say something so stupid in this because I'm gonna try and say something smart, and it's just not gonna come out that way, and it's gonna give us a perfect title for the video.
The Science Salon. Stupid people saying stupid stuff.
Okay.
Stupid people trying to say smart stuff.
Exactly. Okay.
While we begin our way of trying to say some smart stuff.
Okay. Let's try this.
All right.
Okay.
It's weird.
It's black holes are freaky.
Hello and welcome to the Nerdy Wordy, a show where we just have to talk physics once in a while because you know what? We can't just talk about nerd stuff. We gotta do science. We are your hosts. I am Robert.
I'm Billy.
And today we are starting a brand new series on the podcast channel. And I know you have to keep up with all these series, but you know what? You can do it. We are starting a new series called the Science Salon. And no, we are not getting our hair and makeup done. Not even close. Today, a Science Salon in this term is a place where we're going to have an intellectual conversation about things that are occurring during the day.
Mm-hmm.
So anything involving science, anything involving any kind of academia, we'd like to have a very nice civil and productive conversation. And we like to learn some stuff, you know?
Mm-hmm. I just really quickly have to take it back to one thing you said at the very beginning. And anyone who's watching right now should go back after I comment on this and rewatch him say this. Because you said we can't just talk about nerd stuff. We have to talk about physics too. But isn't physics nerd stuff?
No.
No, it's not.
You're putting that into a category that is not the same. There's not the same equivalency.
Okay.
I would say that physics is science and it's not exclusive to nerd culture. The two are not mutually exclusive, I would say, because nerd culture more references popular culture, whereas science is more of academia that's not like, would you really consider Isaac Newton to be a nerd? No, because the nerd culture didn't really exist then. He was an academic, a philosopher. He was someone who was like an important part of his day. So like, I would not consider science to be part of nerd culture. They're not mutually exclusive, but they do have some intersections in there, but they're not the same thing that I would say.
I mean, that's fair. Not every scientist is going to be a nerd.
Right.
I mean, I am.
And
so hence the name of our podcast, right? But
right.
Yeah, I don't know. I always just assumed that they were two sides of the same coin. I guess.
Maybe.
I don't know. Today's one that's very special to Rob's heart. And kind of tangentially. Yeah, well, I mean, it's more of, I think the discussion we're going to have is more of stuff that you find more interesting. Because I'm more quantum. I mean, there's a ton of quantum aspects to what we're going to talk about today. Yes. But I feel like we probably won't talk about it. And maybe we will. Maybe we'll have to do a second discussion on this topic if people want to see a more quantum discussion on it. Because that's my wheel of expertise.
Right. Because
my wheel of expertise. What is that saying?
You're already failing.
English isn't my wheel of expertise. Okay, you talk.
I am going to be introducing a topic involving this topic and quantum mechanics. So you will have at least a little bit of input in your field of expertise. So
Sweet.
nice.
I look forward to it.
So why don't we just talk about the subject? And today we are going to be talking about black holes, one of physics' most interesting and most scary mysteries.
Black holes.
You sound like a supermassive black hole, Billy.
I don't know how to respond to that.
Say thank you.
Thank you.
So
Okay.
I think the best way to start off this salon is explaining to anybody in the audience who doesn't understand what a black hole is. Let's let them know what a black hole is.
Do you want to take this discussion, or do you want?
I think I have the means to be able to describe it to the people. And if you have any more input, I would love to hear it.
Okay, perfect. I love to hear how you explain it too.
So what a black hole is basically this area of space that has such a large concentration of mass that the gravitational field and the force of gravity with that mass is so large that it warps the space around it very close to infinity, to the point where it's black because of the fact that the light that could have been emitted from it cannot escape. The speed of light cannot escape from a black hole. There are several ways that a black hole can be formed, and we're going to discuss this later on throughout the show.
This is where I'm not familiar with the actual formation. I mean, I have like a general understanding, but I'm really interested on that part because I know about like the most basic black hole there is, basically, because that's all we talk about in the class. The basic one. So, what is a black hole? My description is going to be similar to yours, except I'm going to start my description on Earth with a ball. So picture you're at a park, and you have a baseball in your hand. You're standing there, and you're just tossing it up and down. First, you kind of like do like a gentle lob, goes like a foot into the air, and then you catch it. Then you throw it faster, goes a couple feet in the air, you catch it. You throw it faster, goes a little bit higher. And the faster you throw it up, so the faster its initial speed is, the higher it goes. And once you reach a certain speed, a critical speed, you actually throw it out of Earth's gravitational. What's the word for that?
Gravitational field.
Well, it's Earth's gravitational field goes out for infinity, so it's not really that.
Gravitational, like, I know that gravitational fields and forces are infinite, but like there is a certain limit to how much the gravity affects something, you know?
Maybe I'll just say atmosphere, because I feel like that's okay. So you throw it up and it goes higher, you throw it up and it goes higher, and at some point when you reach this critical speed, it escapes Earth's atmosphere, and now it's in space. And that's going to be its critical, or its escape velocity. That's basically what happens with a rocket. You put a bunch of fuel on it so that way you can launch it up fast enough so that way it escapes Earth's atmosphere and it goes into space. Now, why did I talk about this ball and how you have to throw it faster and faster and faster? The reason is this is directly related to what a black hole is, except the baseball now is a photon, and a photon is a light particle. So if we shine a laser pointer up at the sky, and we're in space, and it's a strong enough laser pointer, we'd be able to see the laser. That's because light is traveling fast enough to leave Earth. But for a black hole, it's not fast enough. Light is the fastest thing we know of, and it is not fast enough to reach the critical velocity needed to escape a black hole. So if the fastest thing in the universe cannot escape a black hole, which is light, then A, it looks dark because we can't see anything from it, because light's not coming from it. And B, nothing else can come from it, because nothing else can go at the speed of light except light. And if light can't escape at that speed, nothing can. Hence we get the name a black hole, because we don't see anything. And now Rob is going to define some terms for us, so that way we can have a detailed description and give you the right facts with the right terminology. We'll try to use it when applicable.
Yeah. So one main term that needs to be described here is Einstein's general theory of relativity, which is the basis for how black holes began. Because the theory of relativity describes how the universe gravitational field works. Is that there's this thing called space-time, which is the interaction between the 3 dimensions of space that we know of and the time that we experience due to the fact that it moves forward. And any massive object, like say the Earth, is like a bowling ball. And you have a very stretched out sheet. You place that bowling ball right on that sheet. There's going to be a curvature of that sheet because the bowling ball has a mass that will affect how the sheet looks. And that's the same analogy that you can use for space-time. You have the Earth, place it in where the space-time is. Space-time will be warped. That will create the gravitational field that the Earth has. So we've already defined space-time and general theory of relativity because space-time is the element that general relativity is used, and time actually gets distorted when you get into a gravitational field. So there have been experiments that have happened on the Earth and up high in the low Earth orbit, where we've been able to track how much the time lapses as you go on Earth and as you travel around Earth synchronously. And there are small, minuscule differences in the time, very, very small, imperceptible. But there's very small differences as you go around because you're not as affected by Earth's gravity when you're more away from Earth. And this is also helpful for us to use in satellites when we have to use global positioning systems or GPS. It's helpful for us to be able to use time clocks on satellites so that way they're more precise because general theory of relativity shows that there's going to be a slight difference between what the time is on Earth and what the time is right above Earth because of the gravitational field that's being warped by space-time.
Perfect. Great description. Awesome. I would just add one interesting thing. This isn't a me quote. This is just a quote I really like. I think it's John Wheeler, but I could be wrong. So I need to fact check this. But basically, the idea is going back to space-time. Matter tells space-time how to warp, and then space-time tells matter how to move. So the Earth will affect the space-time around it, which will then tell the moon how to move around the Earth. Basically, one affects the other, and then it affects back. It's always a two-way street. Physics is always a two-way street. Something affects A. If A affects B, B affects A.
Yep, agreed.
That's all I have to say.
So when we talk about the conditions of a black hole, which is this super massive object that has a large gravitational field that has such a large warping of this space-time due to Einstein's theory of general relativity, we have to define a few other terms for this. So for example, we've already talked about what a black hole is. What we have to define for a black hole is one thing called an event horizon. An event horizon is a particular limit that we can observe and we can be able to mathematically determine as to where there's like this quasi-boundary, I would say, for the black hole, where if you are before the event horizon, you're still in space. You're still in the regular of space and time that we are in now. At or beyond the event horizon, things start to change dramatically for you in terms of space-time, in terms of relativity, because of how concentrated this gravitational well is and how much space-time has been warped. That this event horizon is basically the point of no return for black holes, for any information that comes in or out of the black hole, basically.
Yeah. Back to my analogy really quick. Sorry to interject. So gravitational force decreases as you go away from the concentration of mass.
Mm-hmm.
So, for instance, here on Earth, if I'm standing on Earth, the gravitational force from the Earth is stronger than if I was in a satellite orbiting Earth. So the gravitational force decreases as we move farther away. So that means the escape velocity decreases as we move farther away. So if I was standing on a satellite and I want to throw a ball up for it to escape Earth's gravitational pull or push, because nothing moves by being pulled, you can only push in physics. So gravitational push, not gravitational pull. But anyway, it's a lot easier to throw it from a satellite than it is from on Earth. So the event horizon is when you're farther enough away from the center so that the escape velocity at that point is the speed of light. So when you're outside of it, the escape velocity is less than the speed of light. So you can see and you can escape from there if you move fast enough. Anything that's beyond that or closer to the center, the escape velocity is either c, the speed of light at the boundary, or larger than c, so it can escape. So the event horizon is when the escape velocity becomes the speed of light. It's also called the Schwarzschild radius, just to throw that out there. But I don't think we need to put that term in there. I mean, maybe we can. At least they know it.
I think it's important a little bit.
Yeah. Do you want to know the equation? It's 2 times Newton's constant times the mass of the black hole divided by the speed of light squared. I wrote it down. I looked it up on Wikipedia before we started.
Wikipedia, your most trusted ally.
Wikipedia is pretty good for science stuff, but I can also double check it in there. I mean, usually you just set it equal to 1 in physics. So, no, you don't set that equal to 1. You just set it equal to 2m because you set G and C to be 1. Anyway, that's a tangent. That's not important.
There is something, and this one is actually a little bit fuzzy for me, but the Chandrasekhar limits, I believe. I forget what the actual name of it is.
Can you explain it?
I can't because I think I would get it wrong. I thought you would know.
Well, try and explain it. Maybe I know it not by name.
I think it's the limit as to how large a black hole can be, like the mass of the black hole can be, in order for it to be sustained. You know what I'm talking about?
I've heard of it. I've never looked into it.
So the last term I'm going to define here is the singularity, which is an important term for a black hole because singularity, in my terms, and you can be able to add on or correct me if I'm wrong, but in my understanding, that singularity is this central point for the black hole where there's so much mass concentrated that the limit as the gravitational field goes to infinity, it will approach infinity at a singularity.
Yeah, I mean, I went to it. Yeah, basically, it's when the gravitational force is infinity.
Yeah.
It's a point with no volume, basically. And what does that mean? No clue. It's no volume, infinite mass, infinite gravity.
Yeah.
It's the center of the black hole.
So in this book, The Nature of Space and Time by Roger Penrose and Stephen Hawking, they define the singularity. At least Stephen Hawking defines the singularity. Let's see, where is it? Now, I believe, so definition of a singularity in terms of what Stephen Hawking has defined it as is a space-time is singular if it is time-like or null geodesically incomplete, but cannot be embedded in a larger space-time. So this is a very topological, very intricately geometrical way of describing it. So what basically it means is a space-time is singular, so there's singularity if it is time-like. So if the time, basically, when we were talking earlier about the space and time coordinates being flipped, if the space-time is being flipped to a time-like coordinate, or null geodesically basically means that geodesic is in topology, and in geometry is a straight line, any kind of curved or straight line that can intersect another line, basically.
It's the shortest distance between two paths, and in flat space-time or in flat general oh my and flat geometry, it's a straight line. Going from point A to point B, flat. But like on a sphere, it's not necessarily that. Well, on a sphere it is, I think.
So no geodesically incomplete means that it's basically going towards infinity, I would say, right?
I mean, it's hard because we can take this part out, but really quick, the part before where you say the time-like, time-like is a term in general relativity, and that there's space-like, time-like, and light-like geodesics.
Yeah.
And I always get them flipped.
Okay.
So time-like and space-like, one is if we have 1 point. Okay, we have 2 events happen. And if event A happens and then event B happens. So A happens before B. If A and B are close enough that after A happens, light can get from A to B before B happens. So A can cause B. Then it's light-like or space-like. And then if you get to the point where A happens and B happens before light could get there, then it's the other one.
Okay.
And then light-like is if it's exactly. If light, like A happens, light travels, and then B happens right when the light gets there. So it's used that terminology is used in causality. Because if one's light-like or time-like, I think light-like is A cannot cause B because light couldn't get there. And then, no, that's time-like, I think. If A can't cause B, it's time-like.
I think it makes sense because if A directly causes B in light-like, then it should not directly cause it in time-like if A does not directly cause B in the way that you had described it.
Yeah, well, the only problem is so one is where light has enough time to get to B, and one was where light doesn't have enough time to get to B because the space is so large. And I just can't remember if it's light-like or time-like because I remember that like they're like backwards or something like that. Let me look it up really quick. That's good. I don't know why I get it wrong. In the general relativity class that I sat in, every time you said it, I was like, wait a minute, let me check my sheet. And I had it written down so that way I could check it every single time. So light-like is when there's just enough time for light to get there. So the distance is, so C is equal to D over T. So the distance is C times T.
Okay.
Time-like interval, if the value is positive, then we say the interval is time-like. Okay, so space-like, that's what, okay, so space-like is when they're outside each other's space-time cones, which is just another term we don't need to talk about. But so space-like is when they're non-causal.
Okay.
Okay, I feel better.
So maybe that's a little too technical.
That one I think is a little too technical because
I thought it'd be much easier.
Yeah, I mean geodesic. You did a good job describing geodesic. Just trying to describe, I feel like the light-like and time-like without figures and stuff will be hard.
Right. Because I understood because they had a little bit of figures, but I was just like, I don't know if we could be able to describe it in more of like a general term. So
yeah, this isn't overly scientific. I think. I feel like no one.
It's never scientific.
Yeah, no one watching this is gonna be. I think.
Well, that's why I think one rule of this Science Salon is that no math.
No math. Yeah.
No math, because everybody needs math.
No math and no overly complex descriptions.
Yeah.
Because even like no matter what we could describe integrals as calculating area. We could describe geodesics as short lines.
Right.
We can always come up with a simple description.
Yeah.
Okay.
We're going to find singularity in the best way possible. So.
Yeah, I think you did a bang up job.
Yeah.
I've never used that word before. Bang up job. That phrase, I guess.
First time for everything.
Exactly. Okay, let's get back. I derailed this too much.
So now that we've defined our terms for describing black holes, before we get into the next point, do you have any terms that you'd like to define? Anything that I might have missed?
Not that I can think of. You did a very thorough job.
Okay, good.
There might be one that comes up, but I'll define it if we get there, if I think about it. But I think you did it.
One hurdle passed.
Step 2. What was step 2? And think we make it this far.
Neither did I. So what I'm going to talk about now is how do black holes form. It's very important for us to understand how these form. And there's actually 2 ways that I know that black holes form. First way is the one that I think everybody is more familiar with if you've taken any kind of astronomy class. You may know about the life cycle of a star. And there are different types of stars in our universe. There's like white dwarfs, there are stars like our star, there's stars like red giants, there are stars like, brown dwarfs, which are like protostars, different types of stars out there in our universe. The stars that would create a black hole are the red giants because they have so much mass, they're so large, and their life cycles are so short compared to our star and the stars of like white dwarfs. Because of just how much mass they have, they just cannot sustain their hydrogen helium fusion for so long. So for example, our star lasts billions of years, tens of billions of years in those time scales, whereas a red giant would last probably around 100, maybe 250 million years. It doesn't even last that long, maybe even a billion. It's not very long. Red giants, red supergiants are the ones that die out really quickly, and these are the ones that also produce the supernovas. So towards the end of a life cycle of a red giant or a red supergiant, it'll start to collapse on itself because of a term that we had described earlier in another podcast of hydrostatic equilibrium, where the gravitational force of a star has to equal the pressure force of the gas in the plasma going out. So one's trying to push it in, the other one's trying to push it out. Once the hydrogen helium fusion cycle starts to slow down and not produce as much energy, the pressure inside the red giant starts to decrease, meaning that gravity is going to be winning the battle. And as gravity starts to push it in, it's starting to collapse in on itself, and all the elements are starting to collapse in. And eventually, at some point, it's going to go down to a particular mass, and that mass is just going to explode into this huge amount of energy called a supernova. And you see such brilliances from like Hubble Space Telescope of all these supernovas that are out there and these nebulae. And when this happens, but depending on how massive the star is, it could form a white dwarf, or it could form a black hole, depending on how much mass it is. The more massive a star, the more likely it is that it's going to form a black hole because it's just such a centralized, concentrated amount of gravity at one point. So that's how a lot of the black holes that we know about are formed. Does that make sense?
Yeah, makes sense. Good description as well, too.
So there is another form of how black holes can be created in the universe. And it actually started out closer to the beginning of the universe than you may think. So these are what are called primordial black holes. So we think of the beginning of the universe from the Big Bang Theory, where there's this singular amount of mass and energy at some point in the universe's history that at some point just exploded, expanded so fast to create the universe. And it didn't create the universe in one day, like the planets didn't form in one whole day. That process took billions upon billions upon billions of years. But at the time when the Big Bang happened, at a very small infinitesimal amount of time, like 10 to the minus 35 seconds, very, very small time scales, there's this process in the Big Bang called inflation, where you have the points that is the singularity of where the Big Bang started, the size of probably a marble, expanded out, and in minus 10 to the minus 35 seconds, the smallest form of matter of subatomic particles had just formed. And they're accelerating so fast away from each other. And there's so much energy being caused by this inflation that the quantum effects that we know about today are being affected in the microscopic scales. And due to these microscopic events happening with the quantum effects during this early inflation period of the Big Bang in the early universe, black holes start to form, theoretically. We don't know if this actually happened, but theoretically, it seems possible that black holes form because of these interactions with different quantum particles, affected being in the macroscopic scale. And primordial black holes start forming around the universe. And they happen in the thousands, and they scatter around. And these are the first points at which there's so much concentrated mass, because of course, we had started from the singularity, and of course it makes sense that singularities start to form around other places. And eventually, during the time after inflation, during the part of the universe, these primordial black holes start to form pockets of density and concentrations where they will start to interact with the rest of the matter around the universe. And sometimes black holes can affect large amounts of gas and dust and particles and elements to create galaxies. So for example, the supermassive black hole that is in the center of our galaxy, which is Sagittarius A star, that was formed more likely from primordial black holes affecting the gravitational mass at central points in an accretion disk that formed our galaxy with all this gas and dust that eventually became stars and planets and everything else. And there's so much collective gas and dust at the center that it just formed a black hole. And this black hole started to grow and grow and grow because it starts eating all this gas and dust from the universe. And it grows even larger, and it just concentrates all this mass. And this will get into a topic that we're going to talk about later on, about a theory about dark matter, actually.
Just really quick, before you go too far, explain to everyone what an accretion disk is.
Well, basically, an accretion disk is this surrounding amount of material that's around, let's say, a black hole, for example. So in a famous picture that we have seen a couple of years ago when they had taken a picture of a black hole for the first time, we see the black hole in the center of the image, right? That black hole of voided nothingness. Around the black hole is this accretion disk of all the dust and gas and plasma that's around it, that's surrounding it, this energetic amount of gas and dust that surrounds the black hole. And these are accretion disks that could happen for any point mass, basically. You know, you can have accretion disks for an early solar system where you have a concentrated amount of mass for a star, and it has an accretion disk for all the star dust that it has that could form planets, etc.
Yeah. Okay.
So we will get into
let me ask you this, just so that we can get a little bit more detail on it.
Mm-hmm.
Why can we see why does it glow?
Why does what glow?
The accretion disk.
Because there is the concentrated mass of the black hole bringing in this gas and dust in. So as this gas is starting to swirl around the black hole, it has energy, right? It has a lot of kinetic energy. It starts to glow because of the particles inside the gas are starting to emit light and interact with each other, and because it's going faster and faster and faster around, because it is going at the speed of light almost, because it is around a point mass that is near infinity gravity, then it's going to energetically glow. And that's actually how we can observe certain black holes that we have not been able to observe before. Because if, let's say, we have a star, right? We have a black hole, and then there's this star that's just moving out in space. And this unfortunate little star happens to be in the gravitational field of the black hole. It then eventually becomes sucked in. It starts to orbit around this black hole. And of course, the tidal forces, which are the forces that happen on Earth, where we have the sun and the moon, have their gravities affect our gravitational force here on Earth, and it affects our tides, basically, because of just how much the gravitational force affects our planet. Same thing happens with a black hole and a star. There's so much tidal force on the star that it starts to rip the star apart. And this causes a lot of the plasma and gas to encircle around a black hole. And this starts to form an accretion disk. And we can be able to observe that if this gas starts to go faster and faster and it starts to get swallowed up by the black hole, we can start to see the light be emitted much brighter once it starts to consume the star. And this happens over several days or weeks. We can be able to observe it starts to go brighter. And then once it consumes most of the gas and plasma particulates, it starts to glow back down. It starts to dim a little bit. So that's what the accretion disk basically is, and how it has a lot of this energy, because it's generated from being sucked into the black hole's gravitational field and starts to create this energy around it.
Yeah, so you're saying that like the friction and stuff is just like heating it up, and it's just glowing red hot, I guess.
Yep, that's exactly what's happening.
Okay.
So this idea of primordial black holes being around the universe that are affecting how galaxies are formed. This is actually a very important topic that we're going to discuss a little bit later in the podcast. It's a theory that's for dark matter, basically. And we will discuss a little bit about this, and I want to hear your input on it, Billy.
Okay. I think I know. I think I might know what you're talking about.
Okay, good. So those are the two ways that I know that black holes are formed. They're formed from the deaths of red giants and red supergiants, and from the early formation of the universe, creating these primitive black holes that we started having because of quantum effects happening in the macroscopic scales of our universe. And they just spread out throughout the universe, basically.
Interesting. I have heard of the primordial ones before, only because I remember a little while ago I heard that there's like a problem in physics, like why are the black holes some black holes so big? There shouldn't be enough time for them to get that big, and that's one way to try and explain how some got so big.
Yep, that was actually one of the articles that I read in this scientific potential. Yeah,
it's a very interesting problem. Anywho,
so would you like to get into the dark matter explanation with black holes?
Yeah, let's go in the order of what you think is most interesting.
Well, I think I want to say the best for last, because I think it has a little bit ties to things that we're interested in, Billy.
Okay.
So for the theory about dark matter and how dark matter is formed, what we mean by dark matter is that there's this mysterious, let's say, force that is causing galaxies to maintain their shape without dispersing all their particular matter from the edge of their galaxies, like arms, the spiral arms of like a galaxy, for example. It's not spewing out all of this gas and dust. It's maintaining its shape that we can be able to observe. And we theorize that it's being able to hold its shape together because of this mysterious matter called dark matter. And it's called dark matter because we cannot detect it. We can't be able to see it. We can't be able to use any kind of wavelengths in the electromagnetic spectrum to be able to observe it. It's completely invisible to us, and yet it has some sort of force acting on the galaxy. We can't detect it.
Yeah, exactly. We can't see it we see with electromagnetic waves, so light, basically. Let's do it normal. Let's do what some physicists do and just wrap up the entire electromagnetic spectrum into the term light, just so that way I feel like it would be a little bit less confusing.
Okay.
Some people, for like people who aren't used to hearing that word.
Or if I do say it, I will talk about the different spectra of the electromagnetic spectrum, because everybody knows visible light. Everybody probably knows about like X-rays and UV light and gamma rays and infrared. So I think we'd be able to do that. But I just wanted to generalize it as being electromagnetic spectrum. Basically.
Okay. I'm just so I'm gonna use the word light here real quick because I mean all of them. So all of them, we cannot detect dark matter. That's why we call it dark, because we can't see it with light. The only way we know it's there, or we theorize it's there, is because it interacts gravitationally. That's it. No other way that we know of. It only affects gravity.
Yeah.
And that's why we think it's there. It holds galaxies together with extra gravity that shouldn't be there because there's not enough mass that we can see there. to attribute that much gravity. So then there's something there that we can't see that's affecting the gravity. So we just say, oh, it's dark matter.
Yeah. So there are a few theories about dark matter. There's one about, I think it's called MACHOs. I don't know if you've heard about the MACHOs before.
It sounds familiar. I haven't heard the terms for it in a little while. I know it's an acronym. It's like massive.
Yeah.
I
forget what the acronym means.
Massive non-interacting particle or something like that.
No. So that's something different. MACHOs were actually something else.
Oh, then I may not. I don't think I know it.
It's been kind of disproven a little bit, but it's not really important to the discussion. There's also another one that's called WIMPs, and I think that's what you're talking about.
Oh, weakly interacting massive particles. That's what it is.
So that's been also theorized as being something that like a particle, kind of like the Higgs boson, where that interacts with the gravitational field and the mass that we have, that defines what mass is basically. The WIMP, or the weakly interacting massless particle, is basically this particle that constitutes the whole of dark matter, in that it does not interact with normal matter in the way that we can be able to observe it, but it interacts with it gravitationally. And it has very little mass, kind of like a neutrino, and yeah.
No, it has a lot of mass, doesn't it?
Oh, it does? I thought it was
weakly interesting. I thought it was weakly interacting massive particle.
Oh, it might be massive. Okay.
I think so, but I mean, it's been a while.
It's either it has a lot of mass or it has little mass. It probably has a lot of mass because that would make sense, but I don't
know. We'll fact check it.
Yeah. But those are the two theories that have been put out. But another theory that's been put out is based on primordial black holes. So as I had said before, the primordial black holes get formed in the early formation of the universe, and they get scattered out throughout the universe. And over time, they're going to concentrate in certain density packets throughout the universe.
Okay.
And these density packets can go around where there's another supermassive black hole, like where the galaxy is, right? Mm-hmm. And primordial black holes are actually are theorized to be a lot more prevalent in the universe than we think. Because there's a theory that these primordial black holes are the thing that are causing the gravity to maintain the shape of the galaxy. It's the reason why we have dark matter, because of the gravity of each of these primordial black holes surrounding the galaxy, basically. And the reason why we can't detect them is because they're black holes. We can't be able to detect them, especially if it's in the emptiness of space, you know?
But yeah, you can't really see black on black, right?
No.
Interesting. Can I just make sure I understand what you're saying?
Yeah.
Just a clarification. Okay, so we got the nucleus, which is the supermassive black hole, and then around it are the primordial ones, which are acting
like not where the black hole is in the center of the galaxy, but outside the galaxy itself.
And they're what's adding the extra gravity, not dark matter. So dark matter is not a thing. It's just these black holes that are holding everything together.
Yes.
Okay. Interesting.
So I think, let's see, I remember there was a diagram in here, so I'm going to refer to the diagram in here and it was like, step 1, step 2, step 3 of how it works. So let me see if we can find that.
That is an interesting theory, because that completely just cuts away like dark matter is not a thing. Is that right? Has that been proved, or?
It's not been proved. It's just a theory.
Interesting. But really, actually, I'll tell it after you finish with this.
Yeah. Is that it? Yes.
But there's one I'll just mention it right now. But I'll explain it after. There's one experimental evidence, I think, that might contradict that, but we can talk about it. Maybe it doesn't. But continue.
So this is the diagram that I am referring to here. I'm not going to show it off really. I mean, that much. There's a lot of words here, but
okay.
So I talked about how primordial black holes become, and so I'm going to describe what they're basically talking about when they mean about dark matter being the solution with primordial black holes. So there's density fluctuations of these primordial black holes that have been scattered around the universe since the beginning of the Big Bang. The larger density fluctuations collapse later on and form more massive black holes. These can be made into the supermassive black holes that we have in our galaxy, in other galaxies around the universe. The largest primordial black holes could be seeds for supermassive black holes and galaxies formed a billion years after the Big Bang. And today, the primordial black hole clusters would lurk as unseen dark matter in and around galaxies. So I don't know if I can be able to show this image off. So yeah. So like this is what's being described. So we have these primordial black holes right here, right? Mm-hmm. And they get formed and they can be able to make supermassive black holes. So let's say we have a supermassive black hole for this galaxy, right?
I see. Interesting.
There's going to be the rest of these primordial black holes surrounding the galaxy to create the effect that dark matter has on the galaxy, basically.
That's a really interesting theory.
Yeah, and it would make sense. I think they list like several, they list several different reasons for why it could potentially be for like the microlensing. So what microlensing is basically we have a large object, let's say a planet or a star or something, that affects the gravitational view of how we see stuff behind the star or the planets. Mm-hmm. It bends the light of these planets and stars that are behind it. And using microlensing, we can determine that if something's there, if there's some mass there, if what the light is that's coming in, is it like going towards us, is it coming away from us, what kind of light is it coming from, et cetera, et cetera. Mm-hmm. So you can use microlensing to be able to determine if there are primordial black holes out there. A lot of different reasons for why we can be able to observe and maybe determine that primordial black holes are the reason for why dark matter exists in the universe.
Interesting. That's really cool.
Yeah.
I'm going to ask you a question.
Okay.
Because I don't really know too much about this theory, and I wonder if they talk about it in it. I think there's evidence that when there's two galaxies and they collide, or that they don't they pass through each other. And I remember that somehow there's been evidence that like the dark matter gets mixed together or something like that, and like there's a little bit of like leftover after they pass through or something like that. If they pass through,
leftover?
Like they pass through each other, and then like in the middle or something like that, they can see some sort of gravitational effect happening there without any mass being there or something like that. So like it seems like there's like a trail of dark matter somehow or something like that.
Interesting.
I'm not quite sure. Yeah, I'm not quite sure because the only time I heard about it was a couple years ago. There was a theory for dark matter and dark energy being negative mass, whatever that means. And that was really popular at the time because it explained a ton of stuff. Proof ended up being disproven. And I think one of the reasons why it was disproven was that, because negative mass would not do that. I think.
Yeah, I don't know about that. Like, it would be interesting to see, because I think what's interesting, and I don't know if you know this, but like, do you know that our galaxy is actually going to collide with another galaxy?
In a long, long, long time, right?
Yeah, in a very, very long time. So if humans actually do exist in that very long span of time of billions of years from now in the future, I feel like we would have the advance of technology enough to see what would happen if we don't know what dark matter is by that point, which I feel like we would, but like we could be able to observe the two galaxies, our galaxy and the Andromeda galaxy, which is the galaxy that we're going to be colliding with, when they interact with each other over the millions of years that they start to interact with each other, how the supermassive black holes interact with each other and how the mass interacts for the rest of the galaxy. And if the black hole theory is maybe true, then that means all these black holes are going to be like swirling around this collective, this collective amount of mass and dust that's going to be like being made when this collision of these two galaxies collide. So
It's a. Do you know what the name of the theory is? I might take a look at it later.
I think it's just it's the primordial black hole dark matter theory. I don't think there's a specific name for it.
Interesting. I like that one.
Yeah. 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 There's no specific name for it. But I think it's a really interesting theory.
Yeah, because I mean, dark matter's. I'm sorry, what?
I didn't even think of black holes as being a thing for dark matter.
Yeah, I mean, I heard like there's some theories that you can explain away dark matter with some other stuff. One, general relativity might be wrong. B, something. um, but that's really interesting to me because dark matter is kind of just added into our universe because we can't explain what's happening. So this would be like a nice theory where we don't have to just add in a whole new substance. That's interesting. I like it. It has the Billy stamp of approval.
Approved.
Yep. Grants given.
So I feel like I'm going to say the last theory that I liked when I had read through the stuff about black holes. So we don't get too caught up into too many theories to confuse too many people. If you're going to be already bugging that there's more than just one black hole that we know of in the universe.
Yeah.
The one that I thought was very interesting, and you'll see the connection kind of right away, maybe. I don't know if you will. I think you will.
Okay.
So
putting me on the spot.
And this is the one where we're going to be talking about quantum mechanics as well. So the theory is with you know what a wormhole is, right, Billy?
Yep.
So what a wormhole is basically also known as an Einstein-Rosen bridge, where we have one black hole, and that black hole has so much gravity that it is warped the space-time, and that can warp it to another black hole and make a connection between these two black holes in between large distances of space and time.
Can I just add one thing to that?
Tunnel. Yeah, go ahead.
The two black holes have to be entangled with each other, though. So we got two sets of mass.
That's what we're gonna get into.
Oh, okay. I jumped the gun
then. So,
okay.
So yes, as Billy had suggested, that they should supposedly be entangled with each other theoretically, and this falls into quantum mechanics with quantum entanglements. So
should I explain entanglement then?
I mean, I was going to do it as well because I was also hinting on a quantum entanglement team for a couple of months. So.
Oh, that's right, you were. Yeah, go for it.
Yeah.
Okay. Go for it.
So basically, I'm going to explain this in a very simple way. So let's say you have two pennies. Let's say you have 2 pennies or 2 quarters, 2 coins, right? You flip the 2 quarters or 2 coins, and then you can either land heads or tails. Heads or tails. And we can know the probabilities of each one going to heads or tails is 50-50 for each one. You just keep on flipping heads and tails. In a normal universe, they're not going to interact with each other whatsoever. You're going to flip one independent of the other, and they're going to have their own independent outcomes no matter what. Let's say these 2 coins are entangled in some way, meaning that they can share information between each other. So that way they know what one is doing and they can respond in some way because of that information. So let's say you flip the 2 coins, right? And one goes to heads. That means that the other one will go to heads because they're entangled. So you try again. Flip the coin again. It lands tails, but then you're having the other coin be flipped. That also lands on tails. These 2 coins are now entangled because they're now sharing information. So whatever information that one coin is sharing, the other one's going to be sharing. So if it lands on heads, the coin's going to land on heads. If it's going to land on tails, the other coin's going to land on tails. And it's just going to keep on doing this. So think of this in terms of any kind of quantum particle. If the quantum particle is entangled, it's going to be sharing information with another quantum particle if it's entangled with it. So whatever information it's going to share, the other one's going to understand and respond in an appropriate way to that particle.
Can I just add one really quick thing to that?
Of course.
Perfect. Thank you. So I just want to clarify the word sharing really quickly, because I feel like depending on how it's interpreted, it can produce some confusion, maybe. So they share. Oh, geez, how can I not add in a bunch of quantum jargon here?
Hard, right?
Yeah. So we got two. Okay, so we got we got the two pennies, and they share the same. I don't want to make this too complicated. Okay, let me do it this way. We got two caps. Yeah.
Okay.
We got a red cap and we got a green cap. Okay? I mix them up in my hand, and I put one in my right hand and one in my left hand. So this is the analogy of one penny and another penny. Yes. So if I look at one of them, I'll know what the other one is. So this one's green, so this one's red. But this one does not affect this one. This one does not send information to this one. They don't share in the sense that they don't communicate with each other. So when you say share, it doesn't mean they're communicating with each other. It doesn't mean information is being sent to each other. They share as in the the thing that makes quantum entanglement unique more so than almost anything else is that usually for a coin you can describe the state it's in, which means it could be in a state heads or a state tails. So usually you can have one coin and you can describe it by itself, and if it's not entangled with another coin, describe the other one. You don't need to describe one to describe the other. With entanglement, you need to describe both of them. You can't have a description of one of them without the other. So they always share a state. So if my right hand has a green, my left hand will have a red. That's a shared state. I can't have red and red or green and green. It has to be red, or it has to be green and red, or red and green. So they share a state, but they don't share information. So that they do not communicate with each other. Turning one head, if we go back to the coins really quick, if we have coin A and coin B. If I look at coin B and it's heads, that means I know that coin A will be heads, but it's not heads yet. It's heads when I look at it. So it's weird because then I think we should do an episode on entanglement. Because we have to talk about wave function collapse and stuff like that. So one last thing, I promise, people. So if we go back to this thing, if I mix these up, now I don't know what's in this hand, and I don't know what's in this hand. So right now I can describe this one as being red, and this one as being green, and this one as being green, this one as being red. So it's in a superposition, which means we don't know which one it is, but we could say it's in both of them because we don't know what it is right now. We're taking account for every single possibility right now. Now I look at this one and it's green again. This one is not red. Classically, we would say it's red in this hand, but quantum mechanically, it's not red until I look at it. So now when I look at it, now it's red. And that's the weird part about in some quantum mechanics stuff, because you would think if I'm flipping coins and one lands heads, that means the other one is already heads. It's not. The other one is both heads and tails until we look at it, which is weird and trippy and probably still really confusing for almost everyone listening to this because that wasn't the greatest explanation. So we'll do another one at some point, but it's really interesting. So basically, the takeaway from it is that they're correlated. Their information is correlated, but they don't affect each other.
Yes.
They're not. Correlation does not equal causation. One does not cause the other to turn to heads.
So the basic idea of what we're trying to describe here and what I'm trying to explain is that the wormhole of these two black holes connected to each other through space-time, and it's basically a tunnel between one black hole and another one, can be connected, as Billy had described, and be entangled with each other quantum mechanically. So there's this idea of ER, which is Einstein-Rosen, and EPR, which are these three famous physicists, Einstein, I think it's Podolsky, I think, and Rosen. I'm not sure. Don't quote me.
No, I think you're right. I'm pretty sure.
Okay.
It's the ER equals EPR, right?
Yes. So it's this theory that ER equals
Side
EPR.
note, those two papers, ER and EPR, came out the same year. But they didn't realize that they were related.
Yeah.
Which is crazy.
And it's very important that this theory is out there, because one thing about physicists is that we're trying to determine a grand unified theory, which is this theory that can combine Einstein's general theory of relativity, which is the extremes on the macroscopic scale of the universe, and the quantum mechanics world that we're trying to understand in quantum physics, trying to combine those two and try and understand them together. And this ER equals EPR theory basically tries to explain the two, being entangled in 2 points of space and time, with these two black holes being connected through an Einstein-Rosen bridge, and EPR being that they're quantum entangled, with each black hole having a quantum signature that can be entangled with each other through this Einstein-Rosen bridge.
Very cool.
And the reason why I wanted to describe this is because this sounded extremely, extremely, extremely familiar to what happened in Avengers Endgame, when they went in the quantum realm to go from one point to another point in the quantum realm, and they would be quantumly entangled, and they would have to go through, and they had like the space-time GPS. I was like, that's the thing.
That seems yeah, I agree. I didn't think about that. That does seem very very similar.
Right. Now, of course, that's also assuming, like, we understand that the time inside a black hole is very mysterious, and it would work in very interesting ways relativistically. So that's the one thing I'm like, would that make sense? Because again, we're doing like a time travel, because we're assuming that the two black holes are in the same universe, I would guess, because that also brings up this philosophical discussion. It's like, is our universe so infinite that every single thing that has existed in our universe already has existed and will exist, because of just how infinite our universe is that we can be able to describe?
Yeah. It's weird. But also we have to keep in mind that you can't escape black holes. Even if they're entangled, you're still stuck there. And what's really interesting is with that, like the Einstein-Rosen bridge, which is like the connecting piece. There's this theory out there. I think it's called quantum complexity theory. If quantum wasn't already complex enough, we had to name like a subfield of it. But it's basically that, like, I think it's within this field that the Einstein-Rosen bridge is getting larger with time. So the distance between the black holes is getting larger, and it's getting larger faster than the speed of light. I'm not sure if that's the right way to describe it, but it's basically like the idea if you're on a track and you're running a 100-meter race and you're sprinting, but then someone's making the track longer, faster than you're running. So you're never going to finish the race, because even when you make some leeway, now you're farther away from the target because they pulled it back, kind of thing. So that's one explanation of why you can't travel from one to another, because the bridge to get there is just getting longer and longer, which is interesting.
Because I've also heard that like the bridge is also starting to decrease in size, like smaller, like this.
I've heard that. I can't really explain why, other than like, because if you think of it like taffy, when you pull taffy, it gets thinner.
Yeah.
But like, I don't know if that's a good description for space-time, because I feel like who says space-time acts like taffy?
Well, I mean, I would say that like maybe space-time space-time like.
I'm sorry, you just swore.
I didn't mean to swear. That was me trying to say a word.
I know, I've done that so many times, but it's just funny when it happens to someone else. I'm sorry.
Like I think of, since we had just had the discovery of gravitational waves, we know that there is some sort of like surface tension to space-time. There's some sort of like way that we can be able to describe it as almost like a fluid, basically. You know, it's
Yeah.
kind of like a non-Newtonian fluid if you would think about it that way. That's how I would imagine it. It's like a non-Newtonian fluid. Like it can be liquid. You know what a non-Newtonian fluid is, right, Billy?
Yeah. Like the
Right. If it can be liquid,
cornstarch and water is one way to make one.
yeah. So if it's liquid when interacting. This normally, if you dip your finger in it, it's going to be liquid. But if you apply a lot of force to it, it's going to act like a solid, like a semi-solid, and you can be able to like walk on it. Like people have been able to have cornstarch and water, which is a non-Newtonian fluid, and be able to run on it and be able to stay afloat, which you wouldn't be able to do if you just had water or just had cornstarch. Like those two mixed together would be able to allow you to run across because of just how non-Newtonian fluids work. So that's how I kind of think of like space-time. It's kind of almost like a non-Newtonian fluid that can be able to have like, the force applied to it kind of has like the waves that we see in gravitational waves. And it kind of can be the same way as how like something like an Einstein-Rosen bridge can expand and decrease in size as like the black holes like move away from each other. You know what I mean?
Yeah. Can I ask you a question?
Yeah.
Just about the non-Newtonian fluid part.
Mhm.
What? So you said because it can both have like the hard and the soft kind of thing, uh, to it. Um, but I feel, at least for me, so clarify me if I'm wrong, or at least how you're thinking differently. With like just like
Mhm.
water waves, which is not a Newtonian fluid, um,
Mhm.
like it can be soft, and then when you poke it, which is when like you give it the impact, that's when you get like the rippling waves. So, um, I think that is also a good analogy for gravitational waves. So I'm
Mhm.
uh just trying to understand where you're coming from with the where you need like the hard and the soft part.
So like what I mean like is like, you can pass through space and time no matter what, and you don't have any kind of, you know,
Mhm.
interaction or force because you're interacting with the space time, right?
Other than gravity, right?
That's where the force impact, I mean. So like if you have enough mass and you're impacting the space time so much that it can be able to
Oh,
bend, and
I see what you're saying.
and if you're and if there's like something like two black holes surrounding each other and they're starting to orbit and they're causing gravitational waves, that
Mhm.
kind of disturbs the non-Newtonian fluid of space-time even more, so that way it ripples.
Mhm.
But it's not so much as that like it can just pass right through. The two objects can just pass through willy-nilly, not
I
being able
see.
to interact with it. They have just so much mass and so much force on space-time that they can just interact with it in a different way than you would if you were
I
just
see.
like a lighter object that doesn't interact as much. You know what I mean?
I see. I see. Um,
But again, my analogy is not the same as like probably most people because obviously we think of space time not as a non-Newtonian fluid in that respect. So
yeah.
that was just the analogy that like I thought of in my
Mhm.
head.
That's an interest. I wouldn't have thought of that, so that's really interesting.
Mm,
I also heard this really interesting theory that I want to, or not theory. This really, I really like the description, and I want to get your opinion on it as well. It's kind of, um, it's kind of thinking about how gravity is kind of not like the non-Newtonian fluid, but it's kind of like a way to think about it.
mm,
Um, so everyone has I think it's called a. I'm just going to use the non-science way to say it. Everything has its natural state of motion. So if I drop the
mm,
water bottle, it's falling is its natural state of motion, and my hand here is stopping its natural state of motion. So its natural
mm,
state of motion is just moving on a geodesic through space.
mm,
And to go back to the word geodesic,
mm,
uh, and so like satellites are natural state of motion. They're as long as they don't have jets on or something like that or rockets on. I don't think most do.
mm,
I don't know. But anything anything falling, if something's falling, then it's in its natural state of motion. But me sitting in
mm,
this chair is not because I'm not falling. I'm sitting here. And what's stopping my natural state of motion, or let me say this, what's causing or defining my natural state of motion is the way space-time is structured around me. So the space-time around me is structured to make me want to, let's talk about the water bottle. The space-time around the water bottle is structured to make the water bottle want to fall down. That's why it does fall down, because space-time pushes it.
Yep.
So space-time defines what the natural state of motion is. Now matter, aka my hand, is stopping the natural state of motion. And when you stop the natural state of motion, that's what we call gravity, which is interesting. So gravity is just stopping the natural state of motion that space-time tells you to move. Because like people on the International Space Station feel Earth's gravity even though they're weightless. The reason why they're weightless.
They're not weightless. They just okay. It's hard because like it's not weightless per se. They're just falling and they're accelerating. And they're accelerating to a point where they do not have they can't adhere to anything like they do on Earth. So they're just continuously falling. They're like basically the satellite, and they're just falling through in orbits around.
Exactly. But like,
so they're not weightless per se. They do have the mass. Then they do have mass, and it's not a totally weightless thing. That's been kind of cleared up by like NASA scientists before. That's like it's not weightlessness. It's like near weightlessness.
I guess. So let me clarify what my terminology, because I realize where I think the confusion lies. So the way I'm defining weightless, or the way I'm defining weight, is normal force.
Yes.
Due to gravity. Okay. So normal for people at home, if we decide to keep this part in, normal force is just like the force pushing up on you. So like the chair is pushing up on me. So that's normal force.
Right.
When I stand on a scale, the scale is pushing me up and I'm trying to fall down. And that's normal force. And that will be your weight. So they still have mass. So even if we don't put them on a satellite, let's just say a rock is in orbit. That rock is weightless because it doesn't experience a normal force. So that rock in orbit is its natural state of motion. Nothing's restricting its natural state of motion. But once, say if it's an unstable orbit and it's slowly spiraling in, then once it hits the Earth stops its natural state of motion, and that's when it feels gravitational force or weight. But even when it's in orbit and it's weightless because it doesn't have a weight, if it had a scale with it, they would just go together and it wouldn't have a weight. It still isn't a gravitational field. So weightlessness doesn't mean you're not in a gravitational field. It just means you don't have something stopping your natural state of motion, which is interesting, I think. I'm not sure if I described that well.
Yeah, you did.
Okay, good. I remember when I first thought of that, I was like, oh, that's so weird. That's so cool.
Yeah.
Anywho, that was a big tangent. Okay.
So I thought you had a question for me.
Oh, what's your opinion on that? Sorry. That's what I was going to get. I want to get your opinion on it.
I will make this very brief and simple. I concur.
Okay.
Because I don't know how I could follow up with that.
Okay.
I think you had provided a really good detailed explanation that I don't think I can refute or add on anything.
Okay, well, that's good. Let's just go on.
So do you have anything on black holes, Billy, that you have any kind of questions or want to discuss anything about?
I don't think so, because a lot of the stuff I really am into is like the really hardcore theoretical stuff that kind of needs visuals and math and
that is really, a big no.
Yeah, really robust like technical vocabulary. Look at me I take that part out. That's like me bragging or something.
You know me, I can just do all kinds of math and I have a lot of knowledge about technical jargon. I mean, not to brag or anything, but I have a physics degree.
Oh my god. Let me just try and re-say that.
In a non-bragging kind of way.
Yeah, in a non-braggadocious way.
Yes.
Okay. Okay, so I don't think I have really much to talk about other than what we have, because I really like theoretical stuff, and that's not very practical to talk about without figures.
Or making people fall asleep.
Or making people fall asleep, yeah. Because a lot of the stuff that I'm interested in is like unexplained. So it's like I could bring up the problem, then I can't really tell you what the solution is.
Right.
So
black holes are weird, people.
They're weird. They're where quantum mechanics and general relativity both play really important parts, and we just can't describe them well. Or we can describe parts of them decently, but we don't really know how they act.
And we can observe them too. Just look at the pictures.
Yeah, we can observe the effects that they have on the universe, which is really cool. You should put some of those photos up.
Yeah, put a photo up of that famous picture of the black hole. Which, by the way, I have the New York Times that has like that black hole image on the front page.
That's
yeah,
cool.
I want to keep that.
That's pretty
the
cool.
Newspaper print, and I want to make sure that I have the record for it.
That's pretty cool.
Yeah. I also have the death of Stephen Hawking as well from the New York Times on the front page as well on one of those. So
interesting.
Yeah, I like to keep the things that are scientifically important that the New York Times publishes on there.
Yeah, like if someone had like the day Einstein's theory of general relativity was like proven. It took a little while to prove it, but yeah, that would be
cool. It's not really proven though. It's been confirmed a lot, but it's not been definitively been proven.
Touche.
That's my theory.
I mean, yeah, I mean it's been as proven as much as you can prove anything.
Yeah.
Right. Then we get into this whole philosophical thing about you can't really prove anything. It's been confirmed a lot.
I kind of want to get that newspaper now.
Do you want to?
As I know,
if I talk, can you still hear me? Because then I can fill the space. Wait, we can edit this out. Keep going. Go get it.
I mean, you can talk, but I won't be able to respond because I'm not near the microphone.
Okay, I'll just add a little history tidbit then, which is interesting.
Okay, I will be right back and get that paper.
Okay. So what's really interesting is that so the ER, which is so the ER equals EPR part that we're talking about before, which is where we have quantum mechanics, the entanglement, and the black holes. So the E in both of those is Einstein, and the paper that he published with his teammates actually came out in the same year. So his ER paper and his EPR paper both came out in the same year, and they had no idea that they were connected to each other. And then, like however many decades later, they realized that they're both actually connected, and they make a wormhole, which is really interesting. That you need entanglement to make a wormhole potentially. And also, one more thing. Einstein believed in black holes. He did the math and he found out black holes were a thing. But then someone convinced him out of it. Someone said, no, black holes are just fake. Like they're like a math nonsense thing. Like they just pop out of the math, but they're not physical at all. And I'm not sure if he ever went back to believing in them. So he might not have really believed in them. And they're real, which is interesting.
Yeah.
Okay.
So I have the New York Times here. This is from Thursday, April 11th, 2019. This is the day after the discovery of the picture of a black hole. And right on the front page is the black hole. I love it.
It's very cool. Are you going to get it like framed or something?
I should get it framed because I have this one. I have the one that's for Stephen Hawking. And I think that's, yeah, maybe I should.
Because the only thing I'm worried about. What was that?
This is the New England edition, by the way. It's not like the New York edition because they like distribute it. They have local subsidiaries that distribute different versions of the paper based on like where you are. So that way, it's not like New York is sending it out to everywhere in the United States. They have like subsidiaries that like send it out to different places. So that way, it gets more cost efficient.
Interesting.
Yeah.
I'd just be worried about like the aging paper.
Yeah, luckily, I mean, as you know, I am a comic book collector, so I know the importance of preserving books that do leak oils and stuff like that. But like, luckily, this thing is actually in the same condition that I bought it in.
It
2
looked
years
really
ago.
good.
It is, because it's like, even though it's like next to a bunch of other newspapers, it's still like in its pristine condition. So
Nice.
yeah. So I just want to say the caption for the headline says, "Peering into Light's graveyard, the first image of a black hole."
That's a good head title.
Yeah. All right. I'm done with that. Continue.
I was just going to ask you, actually, you were nice enough to ask me if there's anything I wanted to talk about left. Is there anything that you want to talk about?
For black holes?
Yeah. Was there any last minute topics that you wanted to cover?
Nope. I think the Avengers Endgame EPRE are, I think
ER
those are
equals
great.
EPR.
Yeah. I thought that was going to be the last thing, because they kind of bridged the popular culture nerd stuff to like the science stuff. So that way people are like, oh.
I like it.
Yeah.
And I just want to put a vote to the people at home really quick, just to see. If you can think of another topic, please say it right now. I'm talking to you, Rob, right there. But,
okay, you're talking to me?
yeah, so people at home, this one's for you. So for our next science salon, would you want us to talk about entanglement, quantum mechanic interpretations? So basically the philosophy behind quantum mechanics. So no math, no anything, just talking about how different ways physicists like to think about it. So like,
What do you
worlds,
believe?
yeah, like the many worlds you might have heard on the Big Bang Theory, or yeah, that Rob likes, or some other ones like the Copenhagen that they teach in school that everyone knows is wrong, but they still teach it in school as like an initiation. It's like a hazing ritual, and then you have like Bohmian mechanics. Then you have spontaneous wave function collapse. Superdeterminism is another one. Um, I can't think of any of these names. They're escaping me. It's so late. Um, that's my excuse. It's
No
late.
excuse. No excuse, Billy.
Cubism. That's another one.
That's the one.
And there's another one that I really like that I can't think of the name of, which is destroying me right now. Relational. That's what it is. Relational.
Okay.
So there's a bunch that we could talk about, and we can bring some people on. We'll probably do that one anyway. But if that one you're really interested in, we'll probably do that one next, or we can do something else like entanglement. So entanglement, quantum interpretations. I was thinking maybe orbits, just talking about how orbits work. It'd probably be like a really quick video. Maybe it's one that we could do as like a really short one, like a 5-minute video. And if there's is there one that you can think of for a topic? It doesn't have to be physics also. It could be just another science.
Oh, another science?
Yeah.
Well, we can also talk about other things, like we talk about like philosophy,
Yeah,
because that's kind of goes hand in hand almost with physics. It's critical thinking. Just one is more objective and mathematical based, and one is more of like interpretation and deeper thinking.
Yeah.
Not as much objective mathematical thinking with that one, but still.
Yeah, it's basically what the interpretations is, right? Those are just philosophies of science. Yeah, so then I agree. Philosophies. I like that idea. I'm sure we'll come up with other stuff.
Yeah, absolutely.
Yeah.
We got a lot of science stuff to talk about.
Yeah. If anyone actually has any physics questions, write them down below and maybe we'll make a video on them.
I would love to answer questions.
Yeah.
A lot of people know me as someone who likes to answer questions.
I would love to see what people are asking. And maybe we can do like a 2-parter video where like the first part we explain it in words, and then if it's like a really deep question that you need math to, maybe we can try and do some math for it. We'll put it in like a unlisted video and we'll send it to you. Just kidding. But maybe we could throw some math in there too at some point.
But only addition, subtraction, multiplication, and division. No derivatives.
Yeah, only like algebra. If you know algebra, then you'll be good.
Exactly.
Perfect.
Well, in that case, Billy, I guess the salon has to end its session for today. But you know what? It has to come to an end at some point. And I think we had a really nice discussion about black holes.
Yeah, it was interesting. I learned a lot about the formation.
Yeah, and I learned a lot about quantum entanglement.
I'm a big quantum guy. I did like this whole thing on like entanglement that it was so much fun.
And I'm the astrophysical cosmology guy, so
yeah, it was good because this kind of bridges the gap between us, where you're the big stuff out there, and I'm like the really tiny stuff out there.
Yeah, and it makes sense because you're a really tiny person, and I'm a really big guy.
I was just gonna say, do I want to say that joke? No, I don't. But
someone's gonna say it eventually.
I said it. I set it up. You couldn't not say it.
Nope, I couldn't. It's right there. Well, in that case, I hope you enjoyed this video. I hope you learned a little bit. And if you do have questions or comments, please leave them down below. If you want to subscribe, which you should, please do subscribe, hit that like button. And until next time, stay nerdy.
Stay nerdy. Oh, me trying to do geometry diagrams. I have like 4 things crossed out.
I have a bachelor's degree and I can't draw a triangle. The circle is so hard.
Oh my god, it's so true though.
That's not what you should say. You should say, I can draw circles.
I have a physics degree, not an art degree.
Yeah, he did not like his art class that he did in senior year. So.
Okay, let me clarify this. It's not that I didn't like it. It's just it was art appreciation, and it was just. I feel like it would have been a fun. The teacher seemed really fun. It's just that everything was online, and I was still adjusting to it, and it was too much reading.
Yeah.
If anyone has any questions about what we described today, if we didn't do a good job, let us know, and maybe we can make a post about it. Answer the question down below in the comments. Or maybe we can do another video. An update video, yeah. Or maybe we can do a video on general relativity, so that way we can explain that and then go into black holes or something like that. And yeah, or if we're wrong somewhere and you want to correct us, I'm more than happy to be proven wrong because that means I'm learning. So if we said something wrong, please let us know because I'm really interested.
But again, just know that we didn't really have much of any kind of resources at our hand. We just, did a little bit of research and we just had to spit out what we knew about it. So
yeah, I mean, yeah, neither of us are in the field of researching black holes right now, so I'm really interested to learn some more if any of you have more information out there.